Thank you so much, George. Well, good evening. Thank you all for coming, and thanks, George, for inviting me and for that kind introduction. So today I'll like to tell you how, in fact, all of science, is not just astronomy, is being profoundly transformed by the information technology and computing in ways that we never anticipated. Like many other people in science, I grew up with science fiction. And back in, say, Apollo days, we thought, but today we'll have flying cars and we'll be exploring moon and planets and all that stuff, rocket science. And that's, of course, not what happened. The transformational technology of our era was not rockets or flying cars. It was computers, information technology. So, say if you had a time traveler go from present day back 50 years in the days of Apollo and tell them what the world's really like going to be 50 years from then, a conversation like that might happen. And it reminds me that you have in your pocket a supercomputer that gives you access to all the world's knowledge. And once somebody asked, like, what's the most surprising thing you would tell a person from 50 years ago? So I'll tell them I have in my pocket device that gives me an instant access to all of the world's knowledge. And I use it to look at pictures of cats and to argue with strangers. Progress. But seriously, we do live in a historically unprecedented time. It's like having the Industrial Revolution and the invention of printing press combined and squeezed in a space of a couple decades rather than centuries. Nothing like this ever happened in the history of humanity, and certainly not at the pace that's happening today. So this is a very special time, and it's affecting all aspects of modern society and humanity, including science, of course. So there is the word cyberspace in my title, and what I really mean by this is this metaphorical space of information. And you can think of it as the web today, but there is a lot more behind it, and it's evolving to something else. And essentially, it's becoming the principal arena in which we do everything. We do our work, we play, we contact people, communicate with them. Essentially, all aspects of modern society are migrating into cyberspace, so some interface between physical space and cyberspace. And science is certainly part of that. Well, some years ago, an old late friend of mine, Jim Gray, famous computer scientist, that's his picture in the bottom row, came up with this concept of the fourth paradigm. He said that science evolved through a set of paradigms. The first one was the experimental science, starting even with ancient Greeks, but culminating with Galileo. And then analytical science came about with Newton and Einstein and so on. And both of those are still cornerstones of modern scientific method, experiment, theory. And then in the middle of the 20th century, something new came about, computers. And they were used to solve a lot of numerical equations, a lot of differential equations, model nuclear explosions, or now model whatever you want, number crunching, really. And let's call it von Neumann paradigm. But then in the 1990s, a different kind of computing started to appear, data-driven computing. Because today, if you use computer, you almost never do any computing. You're using computers to access, find, and manipulate information and data. And that's a whole different set of architectures and software and methodologies and uses. And that's what Jim called the data-driven science, or the fourth paradigm of science. And I'll expand a little more. What does that really mean? So let's look at some of the important trends. The most obvious trend, the one encapsulated in phrase big data, which is completely meaningless. Big data is more data than I'm used to deal with, and it's a function of time. But the most obvious aspect of it is that the data volumes increase exponentially. And the doubling time averaged over many different fields is about a year and a half, which some of you will know is Moore's law, that essentially cost effectiveness or power of computing improves at the same pace. So the amount of information in the world more or less doubles every year and a half, or in any science. Think what this means is that in next year and a half, we will generate as much data as in all of the past history. And that growth keeps going on and on and on. Now, those of you who know calculus know that derivative of an exponential is also an exponential, so the data rate increases exponentially. And we have to be able to process the data. Well, this is really getting interesting, but it's not really the data volume, data size, data rate, because Moore's law takes care of that. The same devices that give us the data are also the devices that we use to process the data. So as far as the pipelines are concerned, not a problem. The interesting things start happening, we try to analyze the data, and that is a much more difficult story. A little less obvious trend than just sheer volume of data is that the data quality and informational content and complexity also increase. Complexity has many different ways, but one of the ways could be dimensionality of the data. So in astronomy, before, say, we would do a survey of some kind of objects, stars or galaxies, we might measure a few numbers for each of them. Now we have digital sky surveys that measure hundreds of numbers for each of them, or thousands, and so on. Or if you look at genomics, actually genomic data increase way faster than this. I think their doubling time is less than a year. And if you look at dimensionality of the data space, how many different genes and whatnot, people are talking about tens of thousands of dimensions of data space. This is what makes it interesting and difficult. And the fundamental reason, I think, is this, that if you want to understand complex phenomena, anything biological, say, but even in space, you need complex data. And that's where challenges are. So you can notice several trends that I outlined there, that we transitioned from data poverty to an exponential data glut. And we're moving from data sets to data streams. It's no longer you just collect some data set and that's it. Now we have sensor networks and better devices, and data keep flowing, and the rate increases exponentially. So we're driven towards real-time data analysis and discovery, because if you don't do this, you'll never catch up. So the very concept of data is changing. It's no longer just fixed table of numbers somewhere. It is a much more complex entity that keeps growing and improving and spreading and so on. And this also happens in distributed fashion. In astronomy, it's not like one observatory, many different ones, different sky surveys, different space missions, and so on and so forth. And the experts in a particular field need to obtain and curate those data. And so NASA has different centers for all infrared data, all X-ray data, and so on and so forth. And people who really understand those data, get to work on it. So you can't really dominate things. Now, it used to be that you could have one institution, you can dominate a given field, collect all of knowledge. Those days are over. In terms of the value of the data, well, the data are sort of the empirical basis of science. They used to be currency of the realm. If you want to do science, you have to have data. But just like with money, if the government prints a lot of money and gets into hyperinflation, data are not worth very much. In fact, data are a burden. What's really valuable is the expertise of how to discover knowledge in the data, and that's exactly how it should be. So people sometimes ask me, well, why is this just same old stuff, but with more data? And I can think of 3 different things that are really qualitatively different. The first one is, for the first time in history, we cannot see all of our data. The growth rate exceeds the power of humans to actually look at it. And that's different. The second thing is that information content and complexity increases, which means you can't easily find all that's in your data. So you need machine learning tools and whatnot. And the third and most interesting one is that we can be pretty sure that there are highly complex patterns hidden in these highly complex data that we simply cannot comprehend unaided, that we need to have prostheses added to our brains in form of machine intelligence to help us discover these highly non-trivial pieces of knowledge. All the simple stuff's been done. You know, Newtonian gravity is a very simple formula, works great, but there's never going to be a simple formula for a living cell, for example. So, in fact, it's an even more profound transformation there, but you get the idea. So these are really the elements that are changing here. So typical data gathering process today in astronomy or anything else, it doesn't have to be telescopes, could be gene sequencing machines, could be sensor networks, anything. You first collect a lot of data. Then you go into what I would call data farming. You have to store the data in a way that you understand what's where, how to find it, how to access it, and all that. And we know how to do this. And not always easy, but it's relatively straightforward. Then we get into the more interesting stuff of data mining, knowledge discovery in these complex new databases, which is where the interesting technical challenges come in with applications, scalability of machine learning algorithms, and so on. And in the end, you have to actually understand something about the world. But it's, of course, not a waterfall like this. There are feedback loops all over this diagram. You keep going back and changing things on the basis of what you just saw and approve your experiment and so on. And so there's like this whole ecosystem that keeps churning all the time. Well, astronomy, like other fields, has become very data rich. And most of the data today are generated in digital sky surveys, not pointed observations with Keck telescope or Hubble Space Telescope, but small telescopes that patrol the sky on different wavelengths. Need not be small, could be large. But anyhow, we're now talking about data sets of petabyte scale. And we store these data in archives, and this is getting rapidly obsolete. I would estimate that there were over 100 petabytes of archived data in astronomy. I bet it's actually pushing an exabyte now. Doubles every year and a half, and complexity increases too. And I give you here a comparison, just what does that mean? Terabyte is 1,000 gigabytes, and human genome is less than a gigabyte. And human memory, now I've seen estimates differing by many orders of magnitude, but the median in logarithmic sense is about a gigabyte, which means that your laptop has a lot more memory than you do, and I totally believe this. And another way to look at it is a terabyte is about 2 million books if you just look at text. But pictures contain a lot more bits. And how much data can you process as a human mind? Oh, well, roughly say terabyte per year. A lot less if you're reading text because you can't read 2 million books, and a lot more if you're watching videos, but then most bits in the videos are worthless, right? And so this gives you kind of idea. So see, this is why I said for the first time we'll never be able to actually look at all of our data. So we need machines to help us do this. And of course the trend continues. Under construction now we have this thing called the Large Synoptic Survey Telescope in Chile. You may have heard of the Sloan Digital Sky Survey that really had huge impact in astronomy. Well, this telescope will produce the equivalent of 1 Sloan Digital Sky Survey per night for 10 years. And that's actually not much in present-day terms. Radio astronomers are building this gigantic radio telescope array called the Square Kilometer Array, and the name comes not because it's spread over 1 square kilometer, but because area of the antennas adds up to a square kilometer, and they're spread over thousands of kilometers. In fact, half of it is South Africa and half of it in Australia. They're going to generate an exabyte per second. Exabyte is 1,000 terabytes, million gigabytes every second in just raw bits. Most of those bits will never leave the receiver. They instantly get reduced to much less. But in any case, they'll create many petabytes per year, easily, or maybe even petabytes a day. And so we're getting into the business of throwing away the data, which is anathema to scientists. You never want to throw away the data. But we simply will never be able to keep this up. people who are designing this radio facility also know about Moore's law, and they plotted in semi-log graph, and they figure out when this is built, if you had world's biggest supercomputer, you will not be able to cope with all of the data. So you have to be very clever in which data to keep and for how long, data triage, if you will. NASA is already dealing with this process, with this problem in big way because of the bandwidth. You probably don't know this, but only maybe a couple % of all data taken on Mars, around Mars, actually makes it to planet Earth. Most of it is thrown away. And so now they're using machine learning in situ to decide which data to send back. Well, this is a beautiful picture of the Milky Way from our vantage point of view, not even all of it. And it's actually not a picture of pixels. It's created from a catalog of about 2 billion stars measured by Gaia satellite. And so you just put them down and add up the light. And for each of them, they're measuring a whole bunch of numbers with great precision. And it's completely going to revolutionize our knowledge of our galaxy and about stellar astrophysics and so on. And now we're doing this kind of stuff from the ground. It's hard to do it with spacecraft. But then we do it again and again and again. We pave the focal planes of telescopes with imaging devices. And once you take a picture of the whole sky, what do? Well, you have to take another one. And since the things are moving so much faster, we're moving from the era of panoramic cosmic photography, which is what old 10-year-old sky surveys were, to panoramic cosmic cinematography. We're having movies of the entire sky, seeing things move, like killer asteroids that may hit Earth someday, or seeing things explode, supernovae, gamma ray bursts, whatnot. And the whole universe becomes alive. So there are things that you can see only if you have this kind of time-dependent information that you will never be able to figure out otherwise. Another important part is the universe looks different at different wavelengths because different physical processes emit most of their energy in different parts of the spectrum. And here is a mosaic of images, same piece of the sky near the galactic bulge. The upper left is essentially visible light, near infrared. And then next to it on the right is far infrared. And if you look carefully, the missing pieces from visible light is where dust lanes are that absorb that starlight, emit that light in far infrared, thermal emission. So kind of the opposite of each other. And then on the lower left is emission from ionized gas, neutral hydrogen. Looks completely different from all that. Why? Because that's powered by supernova explosions and young stars and so on. And on the lower right is picturing X-rays. Those are more or less dead stars that are now accreting material and shining in X-rays. So if you look in any given wavelength regime, you're getting partial picture. You're getting highly biased image of the universe, and you have to do this panchromatic view over all of the wavelengths and do data fusion to really capture it all. And moreover, now you have to do the synoptic view of doing the same thing, but many, many times all over and having another axis of time added to all of this. Meanwhile, the theorists were also busy, and they run these gigantic simulations of things like galaxy formation, planet formation, supernova explosions, what have you, by having billions and billions of particles in a computer moving according to the physics they put in, and look what comes out. Now, this is a profound paradigm shift because people are not doing this because they're too dumb or lazy to solve the equations, but because there is no other way to do it. And let me give you a simple example. Newtonian gravity, which every student learns, Kepler problem, 2 points, mass points go around common center of the mass. You can solve that on half a page analytically, and that's that. If you add third mass point, there is no analytical solution in general. And great mathematician Poincaré has proven analytically that there is no analytical solution to a three-body problem over 100 years ago. Now you have a galaxy of a couple of 100 billion mass points called stars colliding with another galaxy of a couple of 100 billion mass points, and so on and so forth. We're not doing this because we are too lazy to solve the equations. We're doing this because the only way to follow these phenomena is to mimic in the computer what Mother Nature does out there. There are no analytical solutions. And this is why there'll never be an analytical theory of biology, for the same reason of complexity. So now a theoretical statement is a data set, a time step of a simulation, not a formula. It's a different way of doing theory. That's the von Neumann paradigm. And now you have to deal with these theoretical data just like you have to deal with real observational data. You have to put them together. And so that things get to be pretty complex. So over the last 30 or so years, astronomy transitioned from what's essentially like subsistence agriculture to the modern mega industrial farming that we have way more data than we actually know what to do with. And all that is due entirely to the progress in information technology, VLSI electronics in particular. Because those are not just CPUs, those are also imaging devices, and result in this doubling every year and a half, Moore's law, same devices. And so now all of the action happens in the data system after the data are collected and archived and then they're analyzed. So essentially, that's where all the science really is, and all this expensive hardware in the front, big telescopes with big cameras, is just a hardware front end. The way we say this is the archive is the new sky and the algorithm is the new instrument. We're observing bits using computer code, and we're learning a lot of new stuff. So here is my oversimplified evolution of data-intensive astronomy, and this is kind of log scale. In the 1980s, we had first digital imaging detectors, CCDs. Astronomers learned how to do image processing. And then, by about 90s, we're getting into gigabytes and starting to do surveys. And so we had to do proper pipelines, and then started getting databases, because once you have tens of millions of files, your old-fashioned way of doing it on desktop with hierarchy of directories doesn't work. And then started moving into machine learning, and now we're getting into the artificial intelligence more broadly. So, and that keeps going over this logarithmic axis. Roughly speaking, every 5 years or so, we increase the amounts of data by an order of magnitude. And it was going on and on and on. So the challenge there, again, is not the data volume, because computers also get better and faster and cheaper, but the data complexity and heterogeneity taken in a different way, with different instruments at different times, something's missing, and so on and so forth. That's where all the difficulties are. So around the turn of the millennium, scientific community more broadly started realizing that, well, there is going to be an issue here. And this concept of virtual scientific organizations came about, not just in astronomy, but many fields. Although astronomy is shown to be like poster child of the cyber infrastructure movement, which amazes me to no end, because I know how the sausage was made. And essentially it was a community response to the challenges and opportunities of the exponential data growth. So this created a new type of organization that's not institution-based, but discipline-based. Virtual observatory does not belong to any given university or national lab or anything like that. It is a collective thing, just like the web does not belong to one website, right? And it grows and changes exponentially and crosses boundaries, you need more computer science and so on and so forth. And some bureaucrats are baffled to know what to do with this. It does not fit in any of the standard pigeonholes of structures or management. NSF tends to be staffed by academics, and they love this kind of thing. NASA is really engineering implementation organization, and they have more difficulty with it. But that's a whole another story. So essentially, this was to be a virtual, single one-stop shopping for all astronomy with rich, massive, complex data sets that a user will sit at her computer and have access to all of the different data sets and combine them and use tools and whatnot. And more or less, this is what we've done. Today, all of astronomical data that matter at all, including older pre-digital data that all got digitized are available online to anybody with an internet connection. The only data are not visible are like latest data with big telescope that have 18-month proprietary period. Other than that, today you can be top-notch observational astronomer, make discoveries, and never see a telescope in your life. And science is none worse for that. So we have built really a global data grid of astronomy. What kind of science do you do this? Well, first of all, you can look at statistical studies, structure of the Milky Way, structure of the universe nearby. You have so many data points that Poissonian errors are no longer important. Systematics are important. The second thing is if you're looking for rare types of objects, rare types of phenomena, 1 in a million, well, you better have many millions of those to find some. 1 in a billion, well, you better have more than 1 billion of objects to look into. Example could be very distant quasars or brown dwarfs or unusual supernovae or things like that that are so rare that you have to be really lucky to find one before. And now we can do industrial approach and discover large samples of exciting, interesting new types of objects. And finally, we have these petascale numerical simulations that we also have to match to the observations. So these are the kinds of things for which you need this type of infrastructure that will combine the data and let you explore it in different ways. Another good example is you may know about precision cosmology from cosmic microwave background. The satellites like Planck and WMAP before it and COBE originally took pictures of the cosmic microwave background sky. And when you turn the contrast knob by a factor of 1,000,000, you see it's not a smooth thermal background, but you have these bumps on, it's like essentially solar photosphere inside out. And those contain a lot of important information about dark matter and dark energy and other important things in the universe. But before you can do that, you're looking through a whole lot of stuff, right? There are things that add energy. There are things that absorb energy. There are electrons moving in magnetic fields shining in radio. There are gravitational lensing effects. There are photons coming into clusters, getting out with less energy. It's called Sachs-Wolf effect. And so on. And so you have to remove all that stuff in order to do cosmology first. And all that stuff is measured with some other instruments in some other wavelengths. And so this is sort of how you kind of peel the onion in order to get to this cosmological core in the middle. So it started first in the US with National Virtual Observatory, which we were joking was like the Holy Roman Empire. It was neither national nor virtual nor an observatory, but it was a catchy phrase. And so many other countries jumped on, had their own national virtual observatories, and there is now this organization called International Virtual Observatory Alliance, which is essentially a coordinating body because the universe doesn't know about national boundaries or wavelengths or even Earth's atmosphere. And so this is the way to kind of get all standards together. And it tends to be a boring work, but they do, it's very important work to do. OK, so we got our data house in order. That has many interesting consequences. Not only it enables people, like say at Caltech or Princeton or Harvard, to make important discoveries, but anybody. And you may know that in the first internet boom, there was this book by Tom Friedman, The World is Flat, how internet technology has leveled the playing field. So you can have small entrepreneurs in India or wherever, start to be really participating in the global economy. Well, sky is also now flattened, that anybody with an internet connection anywhere can do first-rate science. And that's important because the talent is spread much more geographically than money. And so I work for an institution whose business model for last, 60, 70 years was privileged access to the world's biggest telescopes. And so for the last 20-odd years, I've been working hard to undermine this business model and make it possible for anybody else in the world to do just as good science because the data are out there free. Okay. It's not that nice, it's simple, So now we have a blossoming new field of astroinformatics, just like bioinformatics. And all these X informatics are amalgam fields between another big amalgam field called data science, and I'll say something about that, and domain field like astronomy or biology or geology or whatever you want. And the purpose of this is not just to give you access to the data, but to engage a much broader community, both as contributors and as consumers of new tools to discover knowledge, because that's what this is all about. Okay? Data science itself is a strange beast. It's based on computer science, engineering, and statistics, and all kinds of other stuff. But it's not a subset of any one of those. And just like in data science itself, in astroinformatics, we have a whole lot of different pieces inside. You know, the pipelines and the archives and data systems and virtual observatory and so on. And there is a really important subsystem called data analytics. This is all what's all about. How do you actually extract knowledge from these data? And that too has many subsystems, and statistics and numerical methods and visualization and so on and so forth. And so somehow this is the way to organize our methodology of really exploiting these big data sets in discovering new stuff in them. And the same thing applies in other fields like biology and so on. Now, a lot of problems in this business can be expressed in this following manner, that they're kind of problems in a high dimensionality data space. So I told you that in a given, say, sky survey, we would measure several hundred different numbers for each object. Right? And think of it as an Excel spreadsheet that will have several hundred columns and maybe a billion rows. How do you explore that? Well, each of these measured quantities is one axis of this multidimensional data space. They're not all independent, and they're not all important, but you don't always know. And the data now occupy this mathematical abstract space in some non-trivial fashion. They don't fill it up. You know, there are correlations, and there are clusters, and some strange things, and some outliers, and that's where all the science is, right? And so that's what most data scientists and most ex-informaticians are worrying about, and there are many things that were challenging, like how to scale those to large numbers of dimensions and so on. A quick historical note in astronomy. This is Fritz Zwicky, who was the original mad scientist of Caltech in 1930s. He and Walter Baade figured out supernovae and predicted neutron stars, and he discovered dark matter, which everybody ignored until 1970s, and came up with all manner of important other things, including gravitational lensing applications and so on, but he was pretty crazy. So he believed in systematic exploration, came up with this concept of morphological box, which nobody understood, and it's a poorly chosen name. It's what we call observable parameter space today. He even brought first telescope to Mount Palomar to do the survey of galaxies to look for supernova explosions, and in the process also got first maps of the large-scale structure of the universe. Well, now recast in a more modern language, any astronomical observation carves out some hypervolume in the observable parameter space of things that you can be measuring. There is area in the sky, there is depth, there is wavelength, there is resolution, and so on and so forth. And so that tells you where the observations are. And this is how we can compare different surveys and so on. Now, each of these hypervolumes in observable parameter space is populated by objects, sources, stars, galaxies, quasars, whatever. So you measure those, and you have their properties. That's what those catalogs are. And sometimes, just in observable space, you can see interesting things. What's shown on the left is two-dimensional parameter space of colors of star-like objects in Sloan Digital Sky Survey. And the black dots are regular stars. They're missing from the middle part because there's too many dots to plot. And the colored ones are quasars, which look just like stars on pictures, but they're a completely different kind of beast. And so you can then use parameter spaces like this to separate interesting from uninteresting. Sometimes then you can throw in additional information, distances, whatever. So you go from observed quantities like flux into physical quantities like luminosity or mass and so on. And on the right is three-dimensional parameter space of physical properties of so-called hot stellar systems, elliptical galaxies, dwarf galaxies, and globular clusters. And the three axes have to do with their kinetic temperature, density, and size. And you can see they're nicely separated in different groups. So it provides kind of space within which you can try to understand how these systems differ from each other and what's the different physics that goes on. So that's essentially the path from these large digital sky surveys to multi-dimensional data spaces to subsets of that data space where interesting phenomena can be seen. But this is a cartoon of a more general view of this. So you have some 3,000 dimensional data space, which I'm representing a pseudo 3D cube on flat 2D screen, filled up with all kinds of measurements, and most of them are not interesting at all. And there are gaps, and then there are kind of heterogeneities and so on. But somewhere in this high dimensionality space, in some corner, in some subset of those dimensions, there is something interesting going on. A correlation, a clustering, some kind of anomaly. And that's, of course, what you're really after. Now, to do this in brute force manner is prohibitively expensive in terms of computing when you start having hundreds or thousands of data dimensions. The numbers of data points are actually not important. That's easy. It's the dimensionality that makes it really, really hard. Let me give you an example of what this might look like. Say medicine. Suppose there is a big pharma company is testing cancer drugs. And they have fantastic data set on many, many thousands of patients. And they have all of their clinical information, all of their demographic information, all of their health history, all of the genetic information, thousands of different things. And they try a drug, and it turns out, well, maybe it helps 0.1% of all patients, not worth putting into production. But it turns out that in some subset of this data parameter space, it helps 100% of people. So that's what you like to find. The regions where there is something very effective in a particular subset of the data, something highly non-trivial that you can exploit. Now, there are many, many tools in machine learning, which is the set of methodology we use. Hundreds and hundreds, actually, of these different algorithms. And now the skill of modern scientists is to kind of know which does what and which one is applicable in which type of a situation. And of course, I will not go through any of those. But this is what computer scientists have been making over the last few decades. And now scientists in other fields are just slowly starting to adopt and learn and use. And the reason we're not doing it sooner is that, well, I'm sad to say, but professors don't know this stuff. We didn't learn this in school. So who's going to teach our students? So we're making real effort to actually try to train the new generation of scientists and data analysts. Let me give you one important problem. It's very fashionable now. It's quantifying uncertainty. So you have something complex, say climate, numerical models of it or observations. And when people do climate predictions for global warming, say, what they do is they run a whole bunch of different models. And then they take the lowest one and the highest one, and that's your uncertainty band. Well, yes, for that particular computer code and that particular data set. So we all know how to propagate errors. We learned that in Physics 1 lab. We all know how to do Monte Carlo, and we all know how to understand numerical round of errors. But then there are uncertainties due to your choice of algorithm, your choice of workflow, how do you go from one algorithm to another, and so on and so forth. And every one of those choices in a highly complex data analysis adds uncertainty to your overall result. And guess what? We do not have a formal framework within which to estimate this overall uncertainty. Amazing, huh? So this is one of the big, big issues and challenges now, how to incorporate all that. Well, that was actually the easy part. Now, one really important part of discovery process is visualization of the data. And philosophers since time immemorial understood that you never understand something unless you visualize it in some way. Even mathematical structures and objects, you have to visualize in some way. That's the bridge to your intuition. Now, here we have a problem. When it's 2 or 3 dimensions, easy. What if you have 300 or 3,000 dimensions? Now what? Because you have to visualize the data first to see is everything okay. Then you have to visualize data to figure out which algorithm makes sense to use. Then you do something, then you want to see what the results are doing. Then you have to change something. So at every step of data analysis, you have to visualize. And if you have more than 3 dimensions, things can be really bad. And every time you down project from high dimensionality space to low dimensionality space, you smear the information. You lose all the structure. So there is a huge premium on being able to visualize as many dimensions of data space as we can. It turns out that humans can actually understand at a given time up to 10 or 12 dimensions of data space if encoded properly in a cleverly designed visualization. You know, because you have X, Y, Z, you have colors, you have shapes, sizes, whatnot, with glyphs. You can actually encode as many dimensions of data space as you want, hundreds, in a given visualization, but you cannot understand them. You can only wrap your mind around, well, 6 or 8 is easy, but 10, 12, that's the peak. Well, still better than 2 or 3. So here is a typical kind of data plots you see in scientific papers. This is the real data about quasars from some astronomical data set. And it's actually 6-dimensional data set, which is not much compared to, say, 60 or 600 or 6,000. And for 6 dimensions, you can have 15 possible 2D plots, X versus Y. And you can see something interesting happening. There may be 2 or maybe 3 different groups and so on. But you really don't see much beyond it. Well, this is what happens when you look at the same data inside a virtual reality projection where you use X, Y, Z and RGB colors and shapes and sizes and transparencies and colors, and suddenly the data become alive, and you can pack information inside each data point, and you get a much better idea of the overall geometry. You see easily it's 3 groups, and there are some things that don't belong. You know, what's this red cube doing over here? What's in there? And so on. And so that was just a very simple example. So this is another of my pet hobbies of using virtual reality as a new platform for data visualization and understanding. And it's actually bigger than that. If you look at history of human-computer interaction, we moved from the old mainframes where you put in punch cards or something, and then we had actual terminals with a keyboard, and now everybody's got mobile computing devices with pointing, tap, and swish. And what's next? Well, what's probably next is some kind of immersive and augmented or mixed virtual reality. Now the headsets look like that, like scuba masks or helmets, but they're going to get lightweight, easy, small, portable like this within the next several years. Why? Because there are huge commercial drivers to do so. And why is this interesting? Because it gets us into a 3rd dimension, and we're so optimized to live in a 3D space and interact with people and objects and information. And the whole flat paper and flat screen paradigm is just a historical artifact. So I predict that within the next 10 years, VR, AR will be completely mainstream in the same way that you have this miracle touchscreen device in your pocket and you don't think twice about using it. But everybody's going to have some sort of more sophisticated 3D interface, and we'll live in some smooth continuum of fully immersive virtual reality, augmented reality with holograms on top of physical reality, and just real reality. Okay, well, this is what this looks like. We actually done this, and you can visualize all kinds of data, and of course this is flat screen projection, so you don't get the sense of how vivid this is when you're really immersed inside the data space. Like network diagrams, which usually smoosh all of the information on flat surface, suddenly become much more interesting. And you can do everything else. You know, overlay information on top of geographical information, interact with them, interact with machine learning tools, interact with each other. And so we're moving to the situation where scientists will be immersed in their data space, interact with the data, interact with machine learning tools, interact with each other, and their colleagues can be on the other side of the world, but sharing the same virtual space. And we actually commercialized this in a startup company called Virtualytics, which is getting a lot of traction already. And why? Because if your spreadsheet has more than 2 columns, you need something like this, right? And a lot of people with spreadsheets with more than 2 columns. Well, our colleagues at JPL have done a different application. They built virtual Mars. They used imagery from Curiosity rover and Mars orbiting spacecraft to recreate 3D Martian surface. And you put the headset on, and suddenly you're standing on Mars next to Curiosity rover. And you can move, walk around, see things in perspective. So people who drive Curiosity rover, they don't do it real time because of the time delay. So they kind of look at pictures, decide this looks like an interesting rock, let's go there, but no, let's first go over here. So they divided them in 2 groups. The control group did the usual, looking at panoramic photography. They marked a whole bunch of different rocks, and they asked them to estimate relative distances and positions of all these different rocks. And the other half of the group did it in virtual reality. And then they compared the results. And people doing it in virtual reality were 4 times more accurate in making these estimates of distances and positions than people using traditional technique. And so for the last 2 or 3 years, Curiosity rover has been driven in virtual reality. Bet you didn't know that, huh? What we're doing also now as a small project is we're building virtual teaching labs where that's the missing component from the online education, where MOOCs can deliver the content and people can interact with each other using social media, but you can't do hands-on labs. Well, if you can reproduce things in VR, and it's almost like doing the real thing, you can do it anywhere you want. And students at Caltech love to do things at 2 in the morning, and so instead of having to come to class, so there you go. But moreover, you can do things that are impossible in real world. You can shrink them smaller than molecules, and they can enter molecules. You can make them bigger than galaxies, and can walk around the universe. And they can build virtual nuclear reactor, and if it melts down, nobody gets hurt. So we think that there's going to be a lot of excellent use of virtual reality labs, and basically we're leveraging all of the development that the games industry is putting in it, spending zillions of dollars to make this better and more realistic, but we want to use it for educational purpose. Well, we're talking about being able to visualize and see complexity, but you also have to kind of understand it intellectually. And in fact, if you think, what's the science all about? It's about reducing complexity of the world to a small set of rules we call laws of nature, right? And all the simple stuff's been done. So how do we discover these new laws of nature, or important phenomena that are way too complex for us to understand unaided? And this is what machine intelligence comes in. In fact, we've been using it for decades in the form of machine learning. It's just one subset of the broader field of machine intelligence for data analysis, data farming, monitoring things, looking for glitches, and so on and so forth, even writing a code. And we're slowly moving towards a collaborative human-computer discovery, with silicon-based mind and carbon-based minds can work together on doing something that neither of them can do separately. We call it cognition technology, if you will. Well, so quick detour, a brief history of artificial intelligence. It starts, of course, with Alan Turing of the eponymous test, who published this paper in 1950, which really started the whole field of machine intelligence. And then, important contribution by a gentleman named J.C.R. Licklider, who was a DARPA project manager, who, by the way, started internet, so thank him for that. Published a computer called Man-Computer Symbiosis. This was in politically incorrect days, but so that's why he said man, but you get the idea. And he had all of this right. He just didn't have the technology to implement it. Only now we're getting the right technology. We started doing this very early on. Every time you talk to Google, you talk to machine intelligence. or in fact, a lot of e-commerce sites. Well, then, in 98, computer became world chess champion, beating Garry Kasparov. Up until then, people say, oh, computers will never be able to play chess like humans. You know, chess is such an intuitive game. Too bad. Since 98, computers are the world chess champions. And now we can talk to AI. And of course, important milestone in 2012. But here is the really exciting one. In 2016, a program called AlphaGo became world Go champion because people said, okay, fine, chess, but Go is a much more complicated game and more intuitive, and computers will never be able to win that. Too bad, they did. And then a year later, they gave another machine intelligence just the rules of the game. Didn't teach it strategies or different games historically and so on. And the machine invented new strategies and beat the previous AI that beat humans. That, I think, is really, really getting interesting, because when we're building these machine intelligences, we don't want to mimic human mind. We want them to think differently from us. And there is a real example. The machine has invented strategies that smart humans couldn't come up with in 2,000 years. So I, for one, wish to welcome our new machine overlords. But Hollywood's been trying to warn us about this for a long time, and Elon Musk too. And so the connoisseurs of this genre, of course, know which one's the most dangerous. And there is a astronaut killing Hal. And my conclusion is that, well, Hollywood has no imagination at all. And we anthropomorphize everything. We can't think of machine intelligence as something that, other than what's packaged in humanoid form. Well, maybe there is something to it, but here is the interesting point. If you think about this, what we have done is we have created alien intelligence on planet Earth, an intelligence that thinks differently from us. And now we have to learn how to communicate with it and how to work with it and build a collaborative discovery, symbiosis. We're already on that path. We have outsourced all of our memory to Google. Nobody bothers to remember anything anymore. You just look it up. So we'll keep going on that. And ideally, the Skynet's going to come up alive, and machine intelligence will really work with us to make something bigger and better. On the other hand, maybe machine intelligence will turn on the news and decide to exterminate humanity, but that's another. So remember the fourth paradigm, the new way of doing science? Well, I think it really boils down to these three things. First of all, there is so much information in modern data sets that you can do profitable data mining, find diamonds in the dust. You know, when I was a kid, I watched Snow White and the Seven Dwarfs. I thought that's how we find diamonds. They're already pre-polished and fist size. You just pull them out of the mud. Second thing is the data fusion. Remember panchromatic universe. There is knowledge hidden in the data that is not recognizable in each data set separately, but when you put them together, it stands out. Astronomers have been doing this since 1960s. Radio astronomy and optical sources, and X-rays, and gamma rays, and so on. So quasars is a great example. They were actually noticed in 1920s as these funky blue variable stars, but nobody paid much attention. And then in 1960s, when they found out those are powerful radio sources, and they're really far away, and therefore you get luminosity 1,000 times the entire galaxy squeezed in the volume of the solar system, it was a new phenomenon of nature, and it was just simplest data fusion. And finally, the third point, that we can now find things that are too complex for us to do without machine intelligence help. So those three pieces really form what I think is the fourth paradigm. One last quick subject, data science methodology transfer. So why should, some fields are ahead of the others, and again, to my never-ending pleasant surprise, astronomy is ahead of most. So why not try to port same solutions from one field to a different field? Because at some point, it's all data vectors or ones and zeros. Why commit same mistakes again. So in other words, this is sort of, remember the whole thing of pipeline. You have to store things in archives, do data analysis, and so on. Well, can you map much of that structure from one field to a different field, from astronomy to medicine, from astronomy to biology, or whatever? And the answer is yeah, to some point, yeah, maybe. So it turns out that genomics has more or less the same data challenges that astronomy had 10, 20 years ago in terms of organizing data and so on. And so with a former astronomer, Aaron Golden, and his boss, John Greeley, we wrote this kind of white paper about astrogenomics, how this can use virtual observatory in exact same packaging to analyze genomics data. And that was the most downloaded paper from the Genomics Journal for a month. And we didn't really say anything like, look, same thing, right? Today, we're working with Earth scientists, building essentially virtual observatory for planet Earth called the Earth Cube, reusing some of the same solutions that were developed for the astronomical virtual observatory. And that's progressing fairly well. It's not terribly different kind of data either. But you can also bottle this in a way. So our friends at JPL have this thing called Object-Oriented Data Technology, or ODDITY, which is open source. And it's been used in at least a dozen different fields to build data systems and even bigger things like virtual observatory, and got awards and so on. And one of those is building a little virtual observatory for a particular type of cancer research. The Early Detection of Cancer Research Network, and they use biomarkers to figure out, to try to diagnose cancer as soon as possible, thus improving the likelihood of survival enormously. And so we just essentially remapped a lot of their structures into things like virtual observatory, and it works. So you have this community, which is maybe several hundred, maybe a couple thousand researchers of this particular branch of cancer research are using this daily. And it's probably more important than anything we've done in astronomy. Here is another interesting one. Look at the chain on the bottom. We have these sky surveys that look at sky repeatedly, look for things that go bang in the night, try to classify them, are they interesting, not interesting. If they're really interesting, then decide whether you want to turn big guns like Keck telescopes on. There is a lot of different kinds of problems like this, that you have to go from vast amounts of potentially, but mostly not very interesting data, to discover a few that are really interesting, and you don't want to miss any, and you don't want to have any false alarms. Like airport security cameras looking for those few faces that you really don't want to get on a plane, for example, right? Well, scientists from our center, Julian Bunn, who is a physicist by training, working with seismologists at Caltech, figured out a way to use cell phones as earthquake detectors. Each cell phone has an accelerometer in it, individually too noisy. So they have a cloud-based system whereby they figure out which cell phones are at rest, like sitting on a table somewhere as opposed to being in bus. And then they average signals from thousands of cell phones at rest. And that gives them maps of the earthshake, which are more precise than Southern California seismograph network, which is probably second only to Tokyo. And now, not only that, but because earthquake waves go at the speed of sound in soil, and theoretically, internet speed of light, you can send alerts to subscribers saying, earthquake's coming, and you have 20 seconds to duck and cover, which is a lot better than 0 seconds. So this can be very useful in places like Southern California. And I love this example, so this will be the last one I'll show you. We worked with some neurobiologists at Caltech. Caltech has a great brain research center at MRIs and so on. And so they gave us a toy problem, which is clinical diagnosis of autism. Turns out the way this is done is not very sophisticated. They give a questionnaire to a patient, and like, is this happy face or sad face? Well, just like 30, 50 questions, and they score them all equally, and if it's more than 35, oh, this person is autistic or something. So trouble is every hospital had their own questionnaire. So all told, there are like 600 different questions that were being posed to do this kind of stuff. Well, we took a look, and with 3 different techniques for machine learning that we applied in astronomy and particle physics, we found that 6 questions contain all of the useful information. And everything else is just adding noise. So with those 6, had almost perfect clinical diagnosis of autism as defined by these people. And that was trivially easy to do. We're just limited by the data to improve on this. That was a very simple application. And now we're getting to more interesting stuff of analyzing time series of data cubes of MRI scans of human brains when they show them different stimuli, see which parts light up. Turns out for any kind of stimulus, fear, happiness, whatever, there are 20 different regions in the brain that light up in some sequence. So you're looking at evolution of 20-dimensional vector in some parameter space. And then you have to deproject that to figure out what could be the causal path that happens there. So it's really new science. So just a few editorial comments. First of all, this is not computer science. Computational science is a different story. It applies computer science. And it's not about data. It's all about knowledge extraction. Data are just a step along the way, right? And data are cheap. Expertise is expensive, just like hardware and software, right? Because software is written by people. And now data science is playing the same role that mathematics and statistics played for centuries as being essentially common to all fields, methodological science as opposed to domain science. So I do nothing all day but sit in front of my computer, and all my data and other people's data and all of our literature has been digitized, and computer models and all my colleagues are behind that screen that I can interact with them. And that's what happened. We turn all into couch potatoes. Progress. So here is the key summary here. The cyberspace is this new arena in which everything happens now, including science. And science evolves, scientific methodology evolves. And it's powered entirely by the progress in information technology today. There used to be different technologies in the past. And so it's not all about handling exponential growth of data. It's really being able to discover actionable knowledge in these increasingly complex and more massive data too. And of course, all of that gets to be applied in the real world too. I mean, the web itself was initially developed to share physics preprints, and look at it now. So everybody has the same kind of data problems. People selling stuff online, security, you name it. Everybody has similar kind of data problems, and with methodology transfer, we can kind of help each other move ahead. So that's it, and thank you so much. It's been a real pleasure. Okay.
Yeah, I do have a question about image. So you guys, I assume you guys deal with a lot of image data.
Yes.
So for that image data, it is very hard to index it because for your pipeline of archiving data, streaming data, and then your pour data into your model, develop your model. So my question to you is, how do you guys index data, especially for image data?
Oh, it's actually fairly easy for us because we do image segmentation, because there are individual sources in the sky, stars, galaxies, whatnot. And software finds those and measures their properties, and they are fed into the data catalog database. But there are also applications where we don't do that, and it's really just images themselves. The metadata we collect are, well, where is it in the sky, when was it taken, which filter, and so on and so forth. And we're playing with some pattern recognition tools to find particular kind of structures in them. But you always go from higher dimensionality into the lower dimensionality data set that can be indexed.
Yeah, second question I have is, so you guys have a lot of unsupervised learning and supervised learning.
Yeah.
So traditionally, supervised learning is very hard to get a training data set. So I have been working on a project with the insurance company to classify the roof
Well, no, I mean, what we do is we use superior data for a subset of that. We take spectra of objects. That's we know. This is a star, this is a galaxy, this is a supernova, this is quasar. So we have objective ways of obtaining ground truth, even though it's, of course, not on the ground. And so that's what we use for supervised classifiers. But there are many, many other issues there that we can discuss separately. Okay, that one and over there.
How do you identify garbage in the data? I mean,
Yeah.
in experiments, you have other people actually
Yeah.
look into this. And in analytics, also, you can really understand the data. It's
Yeah.
relation similar.
Yeah.
But with this data discovery, I mean, you have put a lot of blind faith in these data. And how
Well, no, it's an iterative process. I mean, 90%, I would say, of the effort really goes into data cleaning and chasing all these things. And we can use some of these machine learning techniques to look at potentially anomalous things and try not to throw away the real anomalies, but just the obvious glitches. So there is no magic to it. We just have to kind of go back and forth and see what you're doing. This is why visualization is so important. But yes, if you have lousy data, you're going to get lousy results. That's the usual garbage in, garbage out paradigm. But it's actually a little worse than that, because you can have perfect data, but use wrong algorithm and get garbage out. So it's great stuff in, garbage out, because you made wrong choice of the algorithm. Back there.
Do you foresee a kind of a stagnation of this exponential growth of big data due to limitations from material science?
You mean like molecular limits to Moore's law, something like that?
Yes.
People keep predicting demise of Moore's law for a long time now, and yet somehow engineers get to be clever and come up with a different way of doing it. I hate to invoke magic, but quantum computing might actually push us even further out, assuming it ever works. It's a really important question. I mean, at some point, well, certainly traditional lithography is not going to work, right? But people worry about all kinds of different architectures, how to surpass those limitations. Yeah. Yes?
Yes, you talked about the 4 paradigms for science.
Mm.
And obviously, where quantum computing might be able to push that 4th paradigm out further. Is there going to be a 5th paradigm? And have you thought about what that might be?
Yeah, maybe this collaborative human-machine intelligence discovery will be essentially that path. Data-driven science really did not invoke machine intelligence proper, but just, well, data are telling you what's in the data. So you can statistics or machine learning tools. It's possible that will happen. In fact, there are now experiments where we're having machine intelligence tell us how to run the experiment from all, given all of the different factors that are coming in. And of course, what I want to happen is that in the end, that machine intelligence is going to write a paper and the grant proposal and the report thereof. And so I can actually do useful work. Right? Okay, one back there. Right?
So we use visualization to take the data and make it ingestible for human
Mm-hmm.
consumption, essentially. Is there any research that's being done to use visualization techniques to make the data ingestible for further computer analysis? Or is that just general data, like hygiene and maintenance?
Well, yeah, I mean, for data cleaning, obviously. But computers have no problem seeing tens or hundreds of thousands of dimensions, so to speak. They can apply whatever algorithms you want. And if you have it properly structured, what are the statistical criteria that here is something significant, computer can just march through this. So yes, I mean, really, it is bridged to our intuition. We have carbon-based computers in our head with great pattern recognition, and we feed them through vision as opposed through a piece of code that we give to a silicon brains. Right? Let's take just one more. Right,
that wouldn't have been seen in normal observation?
You know, it's kind of hard to pinpoint things because it just becomes the part of the way we do business. And you can say that probably most exciting new results over past decade plus too, maybe have some component of machine learning involved in getting to that result. But still, you know, human scientists are making most of the decisions, although that too, as I said, might go away. All right, so let's call it tonight.